So at the end of last chapter, I was saying that now we're going to be pivoting to talk about fields. And I hope to impart upon you that this pivot is not like a completely out of left field change, and that there are some relationships here that are worth exploiting and exploring. There are at least two senses that I can tell you about right now that I mean by that. The first is that the main object of study for this class is going to be Galois theory, which is the application of group theory to studying problems involving factorization of polynomials. And that's something that I think that we all understand reasonably well. And the natural setting for talking about factoring polynomials is studying fields. So, in some sense, this is a stepping stone to that question. But just more broadly, I hope to impart upon you in these next couple of videos that a good bit about what we've learned about groups, in some sense, will transfer over to the study of fields and to other algebraic objects too, although admittedly, we don't have time to talk about them in our little 8-week dash. But like, there are other algebraic objects out there, like rings and modules, and there's algebras, not like algebra the subject, but there's a thing called an algebra. And all of these things have properties that in some way allow us to do similar kind of basic calculations to groups, but with extra structure involved. And it turns out that fields are probably the simplest way of adding extra structure. So we should start by talking about what a field is. Fields are sets with two operations denoted by plus and times, satisfying. I'm going to write the usual rules. Let's write down what they are. We have associativity. A plus B plus C is A plus B plus C. And how about we make this like a little 2-column thing we got going on here, because we got plus and we got times. And also ABC equals ABC. We have commutativity. Sorry, that's the plus column. A plus B equals B plus A. Here, AB equals BA. We have a distribution rule. The two operations have to be compatible. And they have to be compatible on the left and also on the right. And then we have identity elements. So there has to exist a 0, A plus 0 equals A for every A. And then analogously, there has to be a 1, A times 1 is A for every A. And then lastly, we have inverse elements, namely A plus the additive inverse is 0, and there always is such an additive inverse, and A times A inverse is 1, but A is not allowed to be 0, right? There's no multiplicative inverse of 0. Okay, so what this is saying is a field is a group in two different ways. A field is an abelian group under plus, and then if I take F and I remove 0, this is also an abelian group under times. And then the distribution rule says that these operations are compatible with each other in the way that we're familiar with from algebra. So, in other words, a lot of the stuff that we've been thinking about with regards to groups in terms of the base calculations are going to be possible here. And we're going to be able to study them with similar algebra tricks, right? Like similar types of looking at equations and manipulating them and so on. Okay, so the next thing I wanted to say is that just like with groups, we spent a lot of time talking about subgroups. We can talk about subfields also. Subfield is a perfectly good concept. It means what you think it means. It means a field within a field. Same operations. Same identity. I guess I should say identities. And one of the things that makes fields different than groups is that with fields, we often also think about the other way around, which is we think about field extensions, which is a field containing a field. With the same operations. In other words, I can't really write same without the air quotes because there's new elements. And so, I have to say what it means to be the same for those new elements. But the idea is that in the bigger field, if I look at the smaller field inside the bigger field, the arithmetic is the same. So think about like Q sitting inside of R, right? Or R sitting inside of C. If I do 1/2 plus 1/3 and get 5/6, that's the same thing no matter what context I'm thinking about these in. As rational numbers, as real numbers, complex numbers, it doesn't matter. It's the same way of thinking. Now, this is a little bit new because we haven't been thinking about group extensions. And the reason is because actually group extensions are really hard. The main motivation is studying equations because it turns out that you can write down a lot more equations in fields than in groups because you have two operations. And moreover, because you have all these equations, it's very difficult to figure out how to solve them and to figure out when they are solvable. And so studying solvability of equations is a core theme. And in group theory, we saw that it's kind of hard to solve equations in groups, right? Like you have a pretty limited ability to collect terms together. In fact, you oftentimes just can't. And so the theory of group extensions is really hard in comparison. So there is a theory of group extensions, and it even is related to solving equations in groups. It's just that, typically speaking, people develop a more general theory coming from more advanced mathematics, and then they look back at group extensions. For field extensions, it turns out that this extra structure of solving equations like linear, quadratic, whatever kind of equations that you can get once you have two operations makes it turns out a lot easier to talk about what kind of equations you can get. And so that's going to be one of the main themes that we're going to be looking at in all of these videos because talking about factorizing stuff is basically talking about studying equations. So I think at this point, I've been talking for almost the usual length of one of these little tutorial videos. What I want to do to end this brief explanation, and then we'll continue our crash course in the next one, is show you some interesting new examples. Because I know you guys know that Q and R and C, these are all fields, but there are more kinds of fields too. So I want to show you another important class of examples. These are finite fields whose orders are prime numbers. In other words, we call these FP, which is shorthand for Z mod PZ, as a field rather than just a group. You could still write Z mod PZ if you wanted to. It wouldn't be wrong. Just sometimes people use this notation to remind you that it's a field. So the operations are the usual addition and also multiplication. Sorry, I said the usual, but it is mod P. I guess I mean the usual for Z mod PZ. And properly speaking, there's I got to check all of these things. But first off, we already know all of these are true because we've seen that it's a group, right? I mean, okay, not entirely true because the distribution one is new. But what am I trying to say? Because of our experience with modular arithmetic, I really, really, really hope you guys agree that almost all of these things are obvious. If they're not, don't let me discourage you. Feel free to pause this and either test some of them out or go on the internet and try to find proofs of these things and see if you can follow along and verify them for yourself. Um, but for me, the only one that really stands out to me as not obvious is this one because it's not true in general. So if p is not prime, not all elements of z mod pz. Maybe I should change it. Because that's confusing. How about if q is not prime, not all elements of z mod qz have multiplicative inverses. And so I should show you that, and then I should explain why it's true for prime numbers. And then I think that'll be enough for our first video. So first, consider z mod 6z. I guess we could have done 4z, but let's do 6. 2 times 3 is 6, which is 0. And if this happens, we call 2 and 3, they're called zero divisors because it appears that they divide 0, right? Like in general, if we had a number, I don't know, c, and we had a, b equals c, we would say that a goes into c, right? Because a times b is c. So I'm saying 2 goes into 0, which is like a weird thing to say, but it's what we call them. And zero divisors can't have multiplicative inverses. Because you just get a straight up contradiction. So first a little lemma. X times 0 equals x in any field. And the proof of this is the usual, right? X times 0 equals x times 0 plus 0. How many times have we seen this trick before, right? Where we're doing it with e, where instead of doing e, I replace e with e times e in a group. We're using multiplicative notation. Here I'm doing it in additive notation, but now I use the distributive rule. Now I don't know what x times 0 is because I'm out to prove that x times 0 huge blunder. Why did I write that? X times 0 equals 0. Yikes. Did I say that? I don't know, that came out of my mouth. That's embarrassing. X times 0 is 0 because I use the distributive property here, and now I don't know what x times 0 is, but I can subtract an x times 0 and of course anything minus itself is 0. So x times 0 is 0, which is what I wanted to prove. So possible yikes, but proof complete anyway. All right. So now with this in mind, if I have a zero divisor, like 2 times 3 equals 0, if 2 had a multiplicative inverse, I would multiply both sides of the equation by 2 inverse. And luckily for us, we are now out of the world of groups. So I can write it on, everything's always commutative. So I can write it on either side and stop caring about that. What a relief. In light of the lemma, this is 0. These things have to multiply to 1 because of the identity principle, or sorry, the existence of the identity, and we get 3 equals 0, which is not true. Right, because we just know that's not true in Z mod 6C. So same thing happens in general. I'll let you guys formulate a general proof since I'm just trying to show the ideas here. And with this in mind, let's turn our attention to Z mod PZ now with P prime. And here's my favorite proof of this fact. So what I'll do is prove a different lemma. Namely, multiplication is injective. So we fix any number n and consider phi n equals Sorry, how about I write phi n of x equals nx? Phi n is a function, z mod pz to itself is injective. Why? Let's see. We have phi n of x equals phi n of y, or in other words, n times x equals n times y. And now, if I subtract this over, nx minus ny equals 0, or n times x minus y equals 0. And all of this is happening mod p. Since p is prime, n does not divide p, so n is not a zero divisor, right? Because this is the same thing as being equal to p when you're working mod p. So therefore, even if I don't know what n's multiplicative inverse is, I can still cancel it. So x minus y is 0, or x equals y. Okay, so properly speaking, this proof is a little bit sketchy. You might be a little bit suspicious, but if you go look in Pinter, you can find a proof in Pinter that's correct. So I can let you guys do that if you want to like really triple check this, but I think you probably find this argument to be convincing. Certainly, I feel like it's convincing. Maybe my opinion doesn't matter. But in any case, once I know that this map is injective, let's remember from our review of functions, for finite sets, if I have an injective function from a thing to itself, it's also surjective and therefore bijective. And that's huge for us because what it means is phi, this phi n, is surjective. And so in particular, phi n of x equals 1 is solvable, right? Because it means that this element of the codomain has a pre-image somewhere. And therefore, that the x that you find has n times x equals 1, e.g., that is the inverse of n. So we found it. And so that, together with the verification of all of the operations, which, I claim is straightforward, is a proof that Z mod PZ is a field. And so this gives us a whole new infinite family of fields to look at. And we will be revisiting them in subsequent videos. All right. And so I know that there's quite a bit of crash coursing to do here, but we're already coming up on 20 minutes. So I think this will be a good place to stop. And then one more such crash course video. And then I promise we'll be back to following the usual trajectory for Pinter.